Few people are still coming, so we wait for 2 more minutes.
Sure, no problem.
Okay, then we can start. Okay, so we can start. So Dibyendu will tell us about lattice input to study of Quarkonia and photon rates from QGP. So Dibyendu, please.
Okay, first of all, I would like to thank you for giving me the opportunity to present my work here. So, as Santon said, I want to talk about what Lattice can tell us about the Quarkonia and photon rates from quark-gluon plasma, why this is relevant for the studies of QGP. So, I'll just start from basic and try to first motivate why this is important to study this Quarkonia and photon. So we start from the QCD, basic Lagrangian. So we know that one of the fundamental force of is strong interaction among the four, and this is described by the QCD Lagrangian, which is a gauge invariant Lagrangian. It has this fermionic field which come through the quark fields. Here are the 6 flavors of quarks, and then there is this gluonic field which is like a photon field in QED. Okay, and there is an interaction between this photon this gluon field and this quark field through this covariant derivative here. Okay, and this field strength tensor of this gluon is going to be given by the commutator of the covariant derivative. So this is very similar to QED, and if you want to draw the Feynman diagrams, but there are except two more Feynman diagram that is there in the QCD Lagrangian, which is the gluon self interaction term, which makes the story of QCDs completely different from QED. For example, one of the important fact of these two diagram is that this running of the QCD coupling. So like any quantum field theory, the coupling runs with its energy scale. So in the case of QCD, the coupling is very strong at at low energy, whereas at high energy it's weaker. Okay, and here I have just shown a two loop running of the QCD coupling constant. Okay, another interesting fact of this non-part of this, so QCD is very non-perturbative at low energy. Okay, so and another important fact of this low energy is that confinement. So we never observe bound state of this quark and gluons in a color form, so they are all neutral under a strong interacting force. Okay, so now what we want to do, we want to study this system at finite temperature. So there is regular recipe from statistical mechanics how to put it in a finite temperature way. So we have to calculate the partition function of the QCD Lagrangian. So we calculate the Hamiltonian and then just take the trace. Once we have the partition function, then we can calculate the thermodynamic variables like pressure and energy density using normal statistical mechanics rule. And then we just change the temperature and try to observe what happens to this pressure energy density. And here is a QCD prediction of this pressure energy density as a function of temperature. And as you see that at small temperature, this is basically the pressure comes basically from the gas of hadrons and its resonances, because as you increase the temperature more and more, higher and higher masses hadrons are getting excited and they contribute to the pressure. But at some point there is a rise in the pressure, gradual rapid rise in the pressure, and this rise will continue and it will shows a signal of a transition from this hadronic phase to a QCD phase. And here you can see that all this pressure, energy density and entropy density are going as increasing as we increase the temperature. And here at very high temperature, even at 370 MeV, we see that it's far away from the non-interacting limit. So this is what you would
Hi,
expect.
hi, Devyendu.
Yeah.
Why there is agreement of HRG above TC?
uh, I wouldn't call it an agreement, because this is not a pure phase transition, right? It's just a crossover. So there is no order parameter in this case. So
No. What I mean is that why HRG seems to be in agreement with lattice above TC.
but as I said, there is no order parameter, so the TC is not perfectly well defined here. So after that, it may differ. You can have another. So I could have called it, this is a TC, right? It depends on which observable you are choosing to define the TC. If
Okay.
you have a phase transition, then there is a sharp change, but there is no phase transition, it's a crossover. So you could call it, I can call it TC here, right?
Also, this HRG curve shouldn't be drawn above TC because there it happens accidentally that it will always rise. So anyway, its curvature is
Divergent.
always on the towards the upside. At some point, it will cross the QCD curves. So it is accidental crossing. It has nothing to do with any fundamental physics because it always keeps on rising. And here, of course, the important point, as you already noted, the HRG consists of hadrons which are at zero temperature. But of course, if you go above TC, then they have a very big finite thermal widths. And so this description will not hold good anyway.
Okay.
Yeah, thank you.
Okay.
Sorry, if this TC is not well defined, how is this TC that you have chosen? It means the presented TC, how is it determined?
So you can define another observable, what is called chiral susceptibility. So it is just the derivative of chiral condensate, and from the peak of that chiral condensate, you can just quote a TC there.
But is
But
that related to confinement?
it's a deep question actually. Yes, somehow chiral condensate is related to the confinement, because then it is basically effectively, if you just look into the various kind of models like NGL model, this chiral condensate gives quarks a effective mass, so it is somehow related to the confinement. But whether so confinement is related to another observable which is called Polyakov loop, whether that Polyakov loop changes a sharp change in the case around the TC, but the connection between them theoretically as far as you know, is not well established yet. What is the connection between the confinement and the condensate? Non-perturbatively, it's model dependent.
Okay, thanks.
Sorry, can I ask one question?
Sure.
Okay, just wondering, so the at high T, why does this look like it is saturating and HRG keeps increasing, but why does actual QCD saturate?
So
is there some qualitative reason for it? No.
yeah, so HRG basically saturate, HRG keep rising because you can show that this number of hadrons that with temperature, it exponentially getting larger and larger. Okay, so this is like, and after some time is diverge, after some temperature it diverge, which is called Hagedron temperature. But in the case of QCD, we know that because of the asymptotic freedom at very high temperature, if we go, then the coupling should be small and it should approach to this non-interacting limit because of the asymptotic freedom.
So basically, HRG keeps increasing because the number of hadrons keeps growing, is what you're saying?
Yeah, exactly.
Okay.
It's
Okay.
exponentially going larger.
All right. Okay. Thank you.
Okay. But another important point I could mention, that there is a recent study which studies this QCD equation of state up to electroweak scale 170 GeV. Even in that temperature, there is a finite gap between the non-interacting limit and what lattice predict. So it's really non-perturbative even at that scale.
Okay, that's the reason is the interaction, right? It's never zero.
So there is this mode like called magnetic mode in QCD. They are non-perturbative even at infinite temperature. So they're they don't go away, non-perturbative effects.
But still consistent with asymptotic freedom.
Because the asymptotic freedom is consistent with that, because if you want to calculate the loop diagrams, then the loop diagram will contribute 1 by g squared t, and from the vertex you get another g squared t, and they get cancelled out, and the contribution is of the order of 1. Okay,
I see.
so that's why this is called a Linde problem of QCD. It's a well-known problem.
Sorry, what problem?
Linde problem.
I see. Okay, thank you.
Okay.
Sorry, just I missed one thing. You said
Yeah.
actually HRG is continuously rising because the number of hadrons are increasing. What? I did not get.
Because
Hello?
as you increase the temperature, the more and more hadrons getting excited. But when the mass is
Mhm.
going, the temperature is larger than the mass, more and more hadron is
Mhm.
more it's produced thermally,
But
right?
do you
From
not start defining your Hamiltonian for or this HRG by taking the zero temperature hadrons?
yes,
So where
but
are
there
the
will
new
be
hadrons coming
statistical
up?
to it. So yeah, so this is like statistical mechanics, right? If you have a probability distribution of higher, the total contribution to a pressure will be smaller from a eigenstate at very high energy. As you increase the temperature, the more and more eigenstate will contribute. It's like exponentially suppressed, e to the power minus e divided by t. But
But
is the
typically, I thought actually the hadrons will basically dissolve if you go higher across the deconfinement transition and higher up.
exactly. So that's why HRG diverge, and that's why HRG diverge, and there is a temperature called Hagedorn temperature after which the pressure will diverge, and that disagreement between lattice and this HRG curve shows that there is new kind of degrees of freedom which is not hadronic,
Okay.
and we have to go to different one. That's why.
Okay. Thanks.
I have one question.
Sure.
This P by T4 counts like number of degrees of freedom, right?
And the P by T to the power 4.
Huh.
It's the pressure. It's related to the free energy.
But it also counts for massless case. It counts the number of degrees of freedom, right?
Uh,
Suppose we had only three pions instead of all the hadrons. How the curves would look like? Those HRG curves?
Okay, so at very low temperature, again, it should be 0. Okay, and uh, after that, so most of the pressure in this HRG comes actually comes from pion because they are the lowest mass particle and the higher mass. So I would not see it will be a much different. It if it's pion because it's the most of the contribution to the pressure comes from pion than other
Yeah, your
channel.
explanation for the divergence is because more and more number of hadrons are contributing, right?
Yeah, yeah.
What is the
So
source of their number? I mean, is it diverging this number of hadrons? What is happening?
no, number of hadrons. Yeah, number of hadrons actually exponentially rising, and it's actually diverging. So it will go like e to the power minus e to the
Where
power
they come
something.
from, all these infinite number of hadrons? Where they come
Uh,
from?
so what they come from? Okay, so this argument of this why should rho increases, it comes from a self similarity argument. So you can think of this quark-gluon plasma with little blobs of these hadrons, and using a self similarity argument you can show that this hadron, the number of spectra goes exponentially large as we increase that. But up here this HRG curve is drawn only up to considering whatever hadrons are there in particle data book up to 2 GeV. Okay, so you include all those up to 2 GeV hadrons in this cap. After that, nothing is included here.
Yeah, what is confusing is I mean, all along the
Mhm.
T, your basic degrees of freedom are same, right? U, D, S, and all that you had in the previous slide, right?
Right. That
And
is
in one case, you have infinite number of hadrons. That's a bit confusing.
uh, because I mean, you can consider UDS and the gluon, right? There are also glue ball masses, right? There will be a lot of hadrons you can consider out of it. Okay, at
They would
zero.
all have different quantum numbers, right?
Yeah, you can contribute. Everything will be included in the pressure. You can consider as many as hadron you want, right? Why should be a limit to the hadrons? I don't know.
This
Sorry,
is the famous
just to clarify.
hadron argument. Yeah.
And then just give me a second. Just to clarify. So as the HRG curve changes across the temperature, your number of hadrons also changes. Do you mean that?
Right.
Okay, thanks.
It is not the number of hadrons. The number of hadrons contributing to thermodynamics changes. The number of hadrons are always exponentially large. How many of them, as he already mentioned, how many of them contribute to thermodynamics depends on what temperature you have. So that's the whole point of it.
So there are more hadrons than there are in the particle data booklet?
Yes, of course. You have huge number of tower of excited states resonances. And in fact, you can see that in the strangeness 2-3 sector, there are lots of resonances which are not yet discovered but known from quark model or lattice data. Similarly, it's true for charm, and that's what we showed long time back, that these are very important for thermodynamics.
Mhm.
Sorry, like you can always pair produce hadron, antihadron, right? And lighter
Yeah.
masses you can always produce, and you can populate more and more numbers of them. That's the way to increase the number, no? You just pair produce lighter
No,
hadrons.
no. Number density will depend on the number of degrees of freedom. This curve is rising because you have different hadrons. Then they are already there at some temperature.
But number of hadrons counting
The
is also
net number should be
counting.
zero. Net number should be zero here, because because we are no chemical potential is adding here. So the hadron particle and antiparticle both will contribute to the same way in this HRG calculation, unless you put a
Yeah,
chemical potential.
but when you are saying number of hadrons is increasing, you don't
Hmm.
mean baryon number is increasing, right? You're only
I mean,
saying number of hadrons, right?
yes,
You
yes,
populate
baryon
more
number is
and more pairs of hadrons and antihadrons at high temperature. You populate more and more numbers, and
right,
that's the
right,
number that this is counting. No,
right. That is the
that
number that is it's goes into the
doesn't
pressure.
mean
Yes.
that you have to have more and more particles from the PDG. I mean, it's just like you can just pair produce lighter hadrons in more and more numbers. But those might be suppressed because they are more massive. The lighter ones are going to be predominantly populated.
But it's not like one pi plus and one pi minus is contributed. This pair production is already included in this QCD partition function through the loops, right? It's all included in the partition function.
Yeah, when you count the number of.
I can't hear. Sorry. Yeah. Can you repeat? I can't hear.
Should continue.
Please use the mic, yeah.
Can you hear me? Sorry.
Can continue. Yeah, please.
Okay. So you see that pressure. There is a change in the number of degrees of freedom here. And if we just calculate what is the energy density that is roughly required for this transition to happen, one can see that this is roughly around 1 GeV per Fermi cube. Okay, so I just wanted to keep this number in mind. Another thing I just plot is this: if we have no interaction and no mass in the particle, then we know that this this relation, that energy should be 3 times the pressure in the case of massless limit and non-interactive limit. So E minus 3p is kind of giving you how much interaction strength is there in the QGP, and which is plotted here, and we can as a function of temperature, and we can see that as near TC, this interaction measure is maximum, and as you increase the temperature, it goes down, which is expected because of the asymptotic freedom, but the non-perturbative effect is really maximum in the in near TC. Okay. So now this is all theoretical study of QCD, but how do we study this system experimentally? So there are ongoing experiments going on.
Sorry,
We are,
can I ask why is E minus 3p a measure of interaction strength?
because if you have a free gas, no interaction at all, and no scale actually at all, then the equation of state we can just calculate trivially from statistical mechanics, and we can see that they follow this relation, E equal to 3 times P. Okay.
Yeah, but
And
that is true of a relativistic gas, right? But if I just have a non-relativistic gas which is non-interacting, pressure is zero, but then it is not any measure of interaction, right?
yeah, in that case it is not, but here it is, everything is relativistic. So in this limit it is E equal to 3p if you have a relativistic gas of boson or particles, let's say.
But this is just coming from relativistic kinematics, that E minus 3p is zero.
Exactly, this is
How is
relativistic.
it anything to do with interact? If you have non-interacting gas, which is relativistic, I'll still have this to be 0, right? And you're saying that if I have interaction, then it'll deviate from 0. Is that what you're saying?
Exactly,
Even if it is
exactly.
relativistic. If it is a
Even if,
relativistic gas but interacting, you will say E minus 3p is non-zero. Is that the claim?
exactly, if it is a
Okay.
relativistic gas which is non-interacting, then it is 0. If it is interacting, then it's non-zero. Okay.
Yeah, how do I see that?
So if you go to the high temperature, then this is, you should expect this to approach to 0, because of this it should approach to the non-interacting limit. But when it's at finite temperature, or a smaller temperature range, then you see that there is some finite number which is huge around this region, and
No,
that
but
tells you
that you are explaining from just the curve. But from first principles, can I see that if I have a non-interact? No, well, no, but meaning from basic arguments, can I see that if I have a non-interacting gas, that this should be 0, but if I put interactions with the gas particles, that this should be non-zero? Is there a simple argument to see that?
I can give this only that argument that when there is no interaction, then it is equal to 3p. If something non-trivial interaction has to have, if it is non-zero, then there is something, some interaction has gone into it. So
Okay.
than that, I do not know what.
Okay, all right, you should continue. Yeah.
Okay. So this is the so this experiment is these phases are studied in heavy ion collision experiment, which is at REAK has happened is 200 GeV center of mass energy, and at LHC it's 5.02 TeV. What they happen, so they collide these large nuclei, and this and after the collision they form a kind of interaction and pre-equilibrium stage between these various parton in this nucleus, and after the interaction they thermalized, and it's expand hydrodynamically, and a local temperature can be defined, and after some time this hadronization, this equilibrated matter will hadronize, and they free stream to the detector. Sorry. So what happens, how do I study this system? So from what is detected, whatever detected from the detector, first of all I have to ensure that there is a QGP. So there is an estimate of the energy that can be calculated, whatever detected from the whatever particles detected in the detector and with its energy. And it turns out that in the case of REAK, the net energy is produced by these collisions per 5 GeV per Fermi cube, and for LHC it's 17 GeV per Fermi cube. And as I showed there, it's only the for QGP production it's required 1 GeV per Fermi cube. So this energy density is way above what is there, what is required for the QGP production. And then there is this multiplicity, how many particles are produced here, and the number of hadrons that is produced in these collisions is way larger than the PP collision. For example, in the case of REAK, it's roughly 8,000 particles produced, right? In the case of PP collision, is 200 around. Okay, and because of this large number of particles, there is a thermalized medium which produced with a local temperature can be defined, and therefore to study this system, a thermal lattice field theory will be helpful here. So this heavy ion collision experiment has a lot of connection to various other fields of physics. For example, this similar phenomena happens to the early universe case, and then there is this hadronization and phase transition which is connected to the statistical field theory or renormalization group in condensed matter physics. Then there is pre-equilibrium stage, then this is connected to the non-equilibrium physics. So there is a lot of connection if we start to the other branches of physics if we study this heavy ion collision experiment. Okay, so now I come to the main question: how do we study this system phase experimentally? Okay, so for example, here is a cartoon. So the probes which are called quarkonia. So this quarkonia is basically bound state of heavy quarks like charm and bottom quarks, and they produce basically at the early stage of the Hebbian collision because of the large energy, the large collision energy is large amount of available energy just after the collision is there. And once they produce, they propagate through the plasma, and with the interaction with the plasma, some of these particles will melt and some of them may survive. So as a result, the number of particles that you would expect will be smaller. Okay, and the reason of this fact, the interaction with the QGP can be understood in the following way. For example, the mass of this quark is much greater than the T and this non-perturbative scale lambda QCD, and therefore you can define a potential between this quark-antiquark pair. For example, here it is shown is this this curve is this potential below TC when there is no quark-gluon plasma. It shows a confined behavior. It's with a linearly rising string tension, and there is a you can calculate a bound state problem within the Schrodinger equation, and you can find there is a hadron like Quarkonia there. But once you are above TC, you would expect this potential to get screened because of there is a other medium in the medium, and this bound state is no longer supported, and therefore there should be a decreasement of the number of Jepsai in the Quarkonia in the medium. Okay. So as a result, the number of quarkonia that you would expect from Hebbian collision will be much smaller than what we would expect from the proton-proton collision, and that is what exactly we see in the experiment of CMS. So here I have plotted this function, this number of Jepsai in a dielectron channel. So these peaks correspond to the sorry, it's not Jepsai, it's upsilon, it's bottom anti-bottom pair, and this red curve is basically what you would expect from a PP collision. But in the lead-lead collision, we see a much smaller value compared to the what you would expect from PP collision. And these are the excited state upsilon peak, and you see that they are more suppressed compared to the 1s lowest one. And this is what is sequential suppression that one would see in the in Hebbian collision experiment. And here I have plotted this what is called RAA. RAA is basically number of Jepsai that you predict from AA collision and versus number of that you obtain from PP collision, but multiplied with the number of pure binary collision. So if it is 1, then there is no QGP, because it's just a many body, it's just a superposition of lot of nucleons collision, no collective behavior is there. But if it is less than 1, then we would have a signal of QGP. And from this data we see that RA is plotted as a function of number of participant nucleus, which kind of give you how large the QGP is, what is the volume of QGP. And we see that with increasing volume, the number of this RA is going down, and there is a clear suppression of RA as a function of participant nucleus. And then 1 is suppressed, 2 is suppressed more than 1 is, and this is again the sequential suppression is shown. Okay. So there is the other probes also study to study this QGP, and they are called these direct photons and dielectrons. So because of the thermal medium, a photon can be produced from the medium, and this is very useful. The photon are very useful to study this, because once they created within the plasma, they do not interact with the plasma with a strong interaction. They just go out electromagnetically and can be detected directly to the detector. So by studying photon, we can study the properties of the QGP directly without further involvement of the strong interaction. And here again is a plot shows that the number of expected photon is much larger than what you would expect from proton-proton collision.
And why is there a low PT enhancement of this spectra?
In this region, you mean?
Yeah.
So this curve is basically the basically what you expect from proton-proton collision multiplied by the number of binary collision, this curve. And we can see that in the heavy-ion collision there is a large enhancement of this number of photon, and this large PT behavior is basically the photon that is coming from very early stage of the heavy-ion collision experiment before the thermalization. Okay, and that's basically scaled with the binary collision. With
there should be some small effects due to the non-equilibrium medium that is formed in the initial stages, right?
Yes, so in this reason that they are also included, right? In this reason they are also included. Whatever is not there in the proton-proton collision will also included here. So this enhancement here is due to the quark-gluon plasma and plus some initial non-equilibrium contribution. But this reason is mostly
this proton-proton data is minimum bias, right?
Right.
Okay.
Right.
Yeah.
Okay. So similarly, jet quenching is another observable when a very high energy jet particles moving through the plasma, they interact with the plasma and they deposit their energy, their momentum gets brought in, and by studying jet, we can study this QGP. Means I did not study jet yet, but I will. This is kind of my future research plan, studying jet in the QGP. Okay, so before now I go to this is the basic. I wanted to motivate why this Quarkonia and photons are important for studying QGP. Now I'll go to the theoretical discussion, but before I go to that, I wanted to show you what I have been doing in my research. So my study is based on understanding these probes like Quarkonia and photons from Lattice QCD, and I have worked on this Quarkonia. Basically, it's calculating thermal static potential, singlet and octet potentials, and then their spectral functions. I have also worked on this photon and dielectron rates, and also worked on the screening mass. Screening mass kind of somehow looks into the spatial correlation between these particles. And then I have also worked on in medium bound states involving light quarks inside the plasma. But in this talk, I'm going to focus on mainly on Quarkonia, and if time permits, I'll show some results on the photon rates as well. Okay, so what are the questions that we would like to answer? So assume that we have a quark-gluon plasma at some given temperature. Now, if we throw a quark-antiquark pair in a bound state like Quarkonia, what happened to that pair? How long do they survive, and how do they propagate inside the plasma? And what is the thermal mass because of the plasma interaction from the QGP, because of the thermal interaction from the QGP, what is the change of the in medium mass of this Quarkonia? And so these are the quantities that we like to answer. And all this information of this Quarkonia, of this quark is encoded in the Quarkonia spectral functions, basically. Okay, so let's try to define this problem mathematically. So what we have to study is the correlation function, because correlation function is everything, all the information is included in that. To do that, we create a quark-antiquark pair at some separation at r prime, when the distance between the quark-antiquark is r prime, at some time, let's say 0. And then we propagate this quark-antiquark pair and wanted to look into what is the probability this quark-antiquark pair being at r after some time t. Okay. Then we just calculate the correlation function between them. So the operator that we can use to define this quark-antiquark pair separated by a distance r prime is a quark field here, antiquark field here, that is shown here, and then a quark field here, which is here, and then some link in between, which I shown here. This link is required because the state has to be gauge invariant ultimately, right? And then we just calculate the thermal average of this correlation function between this at r prime at time 0 and at r at time t. So this is the propagation amplitude from r prime to r at time t, and this is the given quantum state of the QCD Hamiltonian. So what is the transition amplitude in that given quantum state? And then we just take the thermal average over it. So it is just the standard definition of the correlation function. Okay, then the spectral function is nothing but related to the Fourier transform of this correlation function at a r and r prime. Okay, and generally most interesting cases happens when we take the r and r prime tends to 0 because of the point source. For example, if we are interested in the case of upsilon, they produce the q bar pair generally produced in the point interaction. So for example, then in this case it will be psi bar gamma mu psi and psi bar gamma mu psi here. So it will be a correlation function between the two electromagnetic currents of heavy quark field. Okay, and this gamma that I have is just basically taking care of the channel, which channel I am looking at. It could be vector channel, which will be most interesting because it's related to dielectron and photon rate. It could be a pseudo scalar channel, then in that case it's gamma 5, and it could be any other channel as well. It also can project you to the singlet and octet state, but I'll come to that later. Okay. Now, how does this spectral function?
Sorry. What do you mentioned about a thermal average? What do you mean by thermal average?
Thermal average is basically, so we have a QCD Hamiltonian, right? It has an eigenstate n, right?
Okay.
So I just create a quark-antiquark pair on that eigenstate by this operator AO, and then I propagate it and find what is the amplitude of and annihilate it after some time. So that is the correlation function, right? A standard correlation function. In the case of zero temperature physics, it's just zero and vacuum. No thermal average is there. But in the case of finite temperature, there will be contribution of propagation from not only the vacuum case, but also from the eigenstate of the other QCD Hamiltonian. Okay, so it just basically trace of rho times this correlation, O times O and OT and O0. This is just the thermal average, any thermal average of correlation function.
You have to tell what is rho.
Rho is basically this density matrix, e to the power minus beta h divided by z. That is rho.
Okay.
I should have written an equation here. Okay.
And
So,
if I may ask one more thing. So this gamma
sure.
you have actually mentioned at the end, singlet and octet. This gamma is basically the spin structure, right? Dirac spin structure.
Yeah, so it should be the direct product of the spin structure and the color structure. So
Spin structure and the color structure, I see.
yeah, so it should be the direct. So in the case of vector channel, I mean the color structure is just identity, and thus this gamma is only the flavor structure.
Okay, would you be discussing about how you get this octet currents?
Yeah, sure. That is one of my important work. Yeah.
Okay.
Yeah.
Can you briefly also mention that what do you learn from this octet channel in brief?
So in the case of QCD, so suppose we have a singlet Quarkonia, Jepsai, it can absorb a gluon from the medium and it transform into a color octet state. Okay. And to define the propagation in that state, we need a potential which is color octet potential. In the case of QGP.
But isn't color octet potential is repulsive or something?
Yeah, it's repulsive. That's but you will know it perturbatively. No, but there is no non-perturbative argument, and it's very non-trivial to put in a non-perturbative language. I'll show how do I manage to do that.
Okay. Yeah.
Octet potential. It's on top of that, it's not gauge invariant, right? So you have to fix some gauge and extract the gauge invariant information from that. So I'll come to that after I first discuss the singlet one.
But it is not surprising because potentials are always gauge invariant. It's not observable.
Potentials are gauge invariant, but the state can be gauge dependent.
Yeah, but in general, potentials are not observable. So in general, in a relativistic setting.
Yeah. So in a relativistic setting, so potential, whatever you calculate is basically the spectral function from the potential. That is unobservable in a sense. That is more close to observable. Yeah. Okay. So first, before I go there, but I should focus how does the spectral function looks like. So for example, at zero temperature, we have this standard Cullen's representation of the spectral function. It just consists of several delta function. Okay, and if I just put it here in the plot, so these delta functions correspond to the bound state. So this is the first bound state, and then the second bound state, and then after that, some time there will be a branch cut which shows the continuum set of states. This is the zero temperature picture at very well known. But at finite temperature, things get non-trivial. Okay, because these peaks gets broadened because of the thermal interaction, and also the mass can be shifted because of the thermal interaction. Also, the continuum can be changed because of the thermal interaction. So there is a typical plot of this spectral function I show, cartoon plot of I showed here in the case of finite temperature. The goal is to extract this finite temperature spectral function from this. Okay.
Sorry, the figure here is schematic, and you assume there are two bound states in zero
Yeah,
temperature.
it's schematic plot. It's just a schematic plot.
Otherwise, naively, one can think only of a bound state, and then the continuum of states starts right after that, right? If you just consider a single bound state and mass m.
Yes, right.
Okay. So is there any particular reason why you consider two bound state scenario here?
It's a cartoon because it's just a cartoon, no particular reason. For example, if we consider the epsilon, then this bound state will be just 1s, 2s, okay, and then after some time, this is the open threshold bound state, like when
Actually,
this
even the 3s and 4s are also bound states in
3s and 4s. 4s might
So
not be that bound. 4s might be very close to the threshold.
very shallow, but still bound states, right?
Still bound,
Bound
but
state.
so
So I assume
it's
you have actually taken inspiration from the charmonium sector, where your Jep psi and psi 2s is bound state. Am I correct?
yes. I didn't think about Jepsai, but it's just a cartoon picture that I wanted to draw. It
Okay.
could be any, it's
Yeah.
nothing. Okay, the goal is to extract this spectral function from lattice. So here, first time I show the lattice correlate, what we calculate on the lattice actually. So on the lattice, we have this correlation function. We calculate everything on the, so okay, I should mention before that. So whatever I showed here is everything is real time, right? In the real, this Fourier transform, everything is going on in real time. Okay. But on the lattice, we cannot calculate things on the real time, but on the Euclidean time. Here is typical plot of a lattice. Here is the spatial direction, and here is the temporal direction. And the total temporal extent is going to be controlled by the temperature. Okay, if we have a very high temperature, then this temporal extent becomes smaller. If we have small temperature, then temporal extent will become larger. And on that lattice, we calculate the correlation function between these two operator. For example, in the case I showed is this quark-antiquark operator separated by distance r. So we calculate this correlation function on the lattice, and we have to do this analytic continuation from the lattice data tau to it by doing that, which is a non-trivial problem. It's really a non-trivial problem because there are a lot of analytic continuation possible that could go through the lattice data. In terms of a spectral function, it can be reformulated in this following fashion. So you have a correlation function, which is an integration over the spectral function with this kernel. So the goal is to extract this rho omega from this CE. So first we calculate the correlation function from the lattice. Then we have to use this inversion relation to get the spectral function using this equation. But it's a problem. First of all, we can see that there is a finite lattice spacing on the lattice. And as a result, the number of data point is limited. So how many data point we can accommodate in the temporal direction is limited. Okay, so there is a discrete values of tau here. And the spectral function is a continuous function in omega. So there is a mismatch in the degrees of freedom. We want to extract more information than we have. On top of that, on the lattice, we always have statistical errors with the correlation function. And this nature of this kernel is like, if we have any small error in the correlation function, it gets exponentially large error in the spectral function. It's particularly because of this kernel. Okay. So to be summarized, if we have a lattice correlator with the error bar, we can have lot of a spectral function that goes through the lattice data and it still satisfies this relation. So we have to put further physics information to isolate what should be the correct spectral function. And this further physics information generally comes either from perturbative QCD by looking some tau structure from perturbative QCD or effective field theory approaches. Okay, so this is the one of the important slide I wanted to show what is the problem with this calculating the spectral function from a given correlation function on the lattice. At zero temperature, it's very simple in this case, because in zero temperature, we know what should be the exact form of this spectral function. So we know what should be the structure. So of this kernel, right? But at finite temperature, because this spectral function gets broadened, it could be non-trivial.
Sorry, a question here. So you mentioned actually the error in C of E of tau, sorry, CE of tau actually gets exponentially larger when you actually transform into the rho. Is there
Exactly.
a way to understand how it exponentially grows?
Because this is a, so if you just let's say if you go to a small temperature, T tends to zero temperature, then you can show that this is just like exponential, it's like a Laplacian kernel, e to the power minus omega tau, right? E to the power minus omega tau. And when you just, you can, there is e to the power minus omega tau. So if you just have a CE tau, and this e to the power minus omega tau on the right hand side gets here, and the spectral function gets exponentially larger from that.
E to the power omega tau.
And is it not the case if you also consider the zero temperature? I did not really get it.
At zero temperature, you have the pure you know from first principle what this CE would look like. It should be a series of exponential, pure exponential, e to the power minus omega 1 tau minus plus e to the power minus omega 2 tau, depending on the energy. And there is a mass gap from omega 1 to omega 2, and you can extract it from the plateau because of there is a mass gap. But in finite temperature, there is this peaks gets broadened, right? And then the plateau will not be there. I will show that there will be no plateau, as you can see in the lattice that I'll show you. And then how do we extract the mass and width from that?
That is because at zero temperature, that is because of your smaller temporal length, right?
So
you don't get to see the plateau because you have very small temporal length constrained by
exactly,
your temperature.
exactly. A small temperature plane, and that is basically the temperature effect. This fact that this became smaller, it's the temperature effect, because temperature effects comes from the boundary. Okay. Is that clear? Can I go
Yeah,
next?
it's okay. You can go ahead. Please go ahead.
Okay. So now I focus on the Quarkonia, and we can try to make the problem of little bit simpler. Now we know that we can, as I said, this mass that generally we are considering because of this of the Quarkonia is much greater than the medium temperature and much greater than the lambda QCD scale, the non-perturbative scale. So we can integrate out this mass by expanding the QCD Lagrangian of this heavy quark and 1 by m, and construct an EFT, effective field theory, which is called NRQCD, non-relativistic QCD. And in that limit, in this non-relativistic approach, we can calculate a potential that describes the quark-antiquark bound state, like a non-relativistic picture. On the lattice, we calculate this potential, and using that potential, we then calculate the spectral function. Okay, so this is the setup. First, construct EFT, then calculate the potential. Potential is just basically the matching coefficient of these EFTs. And then calculate the potential using the lattice. Once we have the potential, calculate the spectral function. Okay, that is the approach. So let's first expand this EFT here. So if we just expand it in 1 by m, we have this Q-cubed heavy quark Lagrangian of the QCD. And here is this quark field theta, and here is this anti-quark field phi. And these are this 1 by m expanded card. Now we can also expand the correlation function in order 1 by m. And it's not very hard to show that in this order, this correlation function satisfy a Schrodinger-like equation. Okay, and the potential enters here, VTR, in the Schrodinger equation. The goal is to, on the lattice, is to calculate this VTR. And VTR basically is related by the Wilson loop on the lattice, because in the case of defining the static limit, and it's related to the static Wilson loop. So in the case of, we create a quark-antiquark pair at some point with a separation R, and then it propagates with the same separation, and we look into the transition amplitude. That is what is the Wilson loop. And the potential is again given by this long time behavior of the Wilson loop. So, but here we really didn't make the problem, we really didn't solve the problem, because again we have to do analytic continuation here from tau to it. And I'll show now how do we perform this analytic continuation. So we calculate the Euclidean version of Wilson loop on the lattice, and then we calculate the we try to do the analytic continuation. But to do that, we need to know some analytic structure. Okay, so first let's see what do we know about this Wilson loop in the Euclidean time. Okay, so it's from very first principle that we have just discussed, that in zero temperature, this Wilson loop is just goes like exponential minus of some number times tau, because it's from very first principle, transfer matrix argument. And this is a pure exponential decay at large tau. And therefore, the potential, this quantity inside this exponential, can be extracted by looking into this following quantity, which is called the effective mass. So it's basically the ratio tau divided by tau plus a. And this ratio, if pure exponential behavior dominates in the correlation function, this ratio will show a constant behavior in tau. Here I show a typical plot of a effective mass from actual lattice data as a function of tau by a, and we can see that below there is no pure exponential decay around 5 or 10 in lattice unit, but after that it saturates a little bit. It's kind of close to the saturate. And this signal there is a pure exponential behavior, the fact that it's saturated. And from that value of saturation, we can extract the potential at zero temperature or 101 MeV. So whenever I call zero temperature, I meant that it's much below the crossover temperature. Okay, and so it's very easy to calculate this potential non-trivially trivially on the lattice at zero temperature. And this limit that defines the potential exists trivially at zero temperature, because pure exponential decay, and you can see I can just analytically continue to tau to it and just calculate this limit. But at finite temperature, as we just discussed, we do not see this plateau at all. What we have is just a gradually decreasing function all the time, and we have to extract the potential from it. Okay, and the reason there is no gradual decrease, telling us there is no pure exponential decay. And how do I understand that? Because why it's not decreasing gradually? It's not showing a plateau. It can be understood that if we just look into the leading order perturbative calculation of this potential, it turns out to be it's not purely real. It's actually complex. It has a real part and the complex part in finite temperature. In the zero temperature, there is only real part. At finite temperature, there is an imaginary part associated with it, and this imaginary part makes the business complicated. And this imaginary part is responsible for the fact that there is no plateau at all. Okay. Now we have this quark-antiquark pair separated by R again, and one intuition we can give that this gluon interaction take place between this quark-antiquark pair, which gives the potential basically, and this gluon has a self energy which is thermal average with the medium, and it has a real part and it has an imaginary part. The imaginary part can be obtained just by cutting it with this standard Kutoski rule. The real part is basically shows the screening of the plasma, and this imaginary part gives the Landau damping. Basically, it shows the scattering of this QQ bar state with the medium partonic modes. Okay, so that is motivated from perturbation theory, this argument, and that is what we want to calculate non-perturbatively on the lattice.
And why is it justified? Because the Landau damping, this comes from the hard modes only. So this picture is justified, right?
Hard modes only. It's the space-like region, right? It's Landau damping happens in the space-like region from gluonic momentum.
But you can calculate it only in the HTL type of picture, right?
Yeah, so you can integrate out this hard mode. So this is the hard mode you integrate out. Okay, that is what you mean by hard mode. Okay, you integrate out this hard mode. Yeah. So right. So this is one of the contribution to the Landau damping. I'll come to it. And there is another contribution to the potential, the imaginary part. It's not only this hard mode Landau damping is going to give you the imaginary, but there is another contribution which I mentioned earlier, that it can get there is a singlet state, Quarkonia, and it can transfer into octet state. And once it transfers into octet state, it just melts. And that is another contribution to the imaginary part. That is not from the hard mode. Okay. Does that answer your question, or?
Yeah, this gives my answer. Yeah.
Okay. So
may I ask a question here? So
sure.
At finite temperature, you get some imaginary component to your potential, which also
Right.
means that you should have some imaginary component in your effective mass as well, right?
Imaginary component, it comes as a but no, the Wilson loop is always real. Wilson loop never complex. Only after the analytic continuation it can become complex, but the effective mass is defined only in the Euclidean time, so it's completely real.
But if I actually plug in this potential V of R on your third bullet back into the Wilson line, back into the definition of W, then basically I have a imaginary component, right?
You cannot plug this here. You cannot plug this in. This argument is only justified when you see a plateau.
Okay.
This pure exponential behavior. But here, like at finite temperature, we do not see a plateau. So we do not have this pure exponential decay. So we cannot just plug it back there. The structure at finite temperature will be more complicated. I'll show next slide. How do I extract this structure? But we cannot do it here.
Okay, thanks. I understand.
Okay.
So Dibendu, you have to, we are already at 3:06. We started at 2:10. So we are almost nearing 1 hour. We will have 15 minutes more. Yeah.
Okay.
Yeah.
Sorry, then I just hurry.
No, it's fine. Just
Okay.
to tell you, you don't have to rush, but just to give you an estimate of time.
Okay. So this is the part I showed, and then how do I understand? So there is no pure exponential decay there, but how do I? But I want to make sure that this limit exists after I take the whatever Wilson line correlator that we have. Then I analytically continue, and then I have a real and imaginary part of the potential. Okay, and there is no plateau behavior that can be motivated from the HTL, again from perturbation theory. We can see that if we look into the leading order perturbative calculation, we see that it consists of two parts. One is the pure linear behavior and another is the periodic part. Okay, this linear behavior is kind of responsible for the plateau, and this part in the periodic, in the Wilson line correlator, the periodic part is basically not let you give the plateau. Okay, that is the responsibility that is motivated from perturbation theory. But does this is this a statement that it is a composition of two part, a linear plus a periodic part, is only valid on perturbation theory? No, it's also valid non-perturbatively. And the way we can check this, and that is one of the work that I did, is that we can take the ratio, non-perturbative ratio, tau and beta minus tau, and then it's purely become exponential. And from this exponential, you can define again an effective mass kind of structure here. If this shows a plateau, then we can see that there is a potential, this structure is valid also non-perturbatively. Okay, so although the effective mass does not show did not show you the plateau earlier I showed here, but once we have this combination, it shows a nice plateau behavior as a function of time. Okay, and this is the analytic understanding that we have performed. And using this analytic behavior, we have constructed this Wilson loop. Again, this is the non-perturbative behavior. Now we confirm it. And this Wilson loop now again given by this exponential of VR tau with some extra term. That is what was Padmanabh was asking me. This is the extra term that has to be put in on top of the pure exponential decay. And that is the part that is not give you the plateau. Okay. So once we have that, we can just feed the lattice data to extract the real and imaginary part of the potential. Okay, earlier it was not known what should be the possible form in the case of finite temperature for Wilson loop. It was only known at 0 temperature, but for finite temperature, we derived this has to be the form, this extra functional form. Okay, now this fits the lattice data very well with a very nice chi-square degrees of freedom. Now I can show you some measurement of this real part and imaginary part by fitting from the lattice data. And here is the first time I perform the calculation of potential with this kind of precision. Here is the real part I show, and here is the imaginary part I show. We can see that this real part is confined behavior, and now as we increase the temperature, it shows screening behavior. Okay, and the imaginary part is, on the other hand, increasing with both distance and time. It is pure coherence, and therefore you kind of use a multi-level algorithm to reduce the error. Recently, this has been promoted to the full QCD calculation with a dynamical fermion, and again we see this behavior that it's confined below TC, and above TC it shows screening behavior. And this potential is basic, and imaginary parts, as always, is giving you the is increasing with both distance and temperature. And in the case of, I should want to mention that in the case of dynamical QCD, we cannot use multi-level algorithm that we have used for coherenced case, but we use something called gradient flow for this error reduction. Okay, but
And do
I
you
want to
understand why in the high temperatures the imaginary part rises very sharply?
why? Yeah, because the Landau damping will contribute more and more, right? Because the hard part, the medium which bombarding the energy on the heavy quarks, has more and more thermal energy, right? They will give you more and more imaginary part. So that's why it's increasing, right?
Yeah.
Okay, so
Here, I have a question here.
sure.
In the case of dynamical fermions, you have this confinement like behavior at 110 MeV, right?
Right.
But that is up to some distance, right? Because there will
Yeah,
be
yeah, yeah.
swing
There
breaking.
will be, yeah, there will be some, after some time it will actually it's saturate, but that will happen roughly after Fermi, right? 1 Fermi or 2 Fermi after lambda QCD scale. But here we have plotted up to 0.8 Fermi. So it's, if you would have plotted it more, then we should show a saturation here.
Have you seen that in your lattice
No,
data?
no, it's very difficult to go in that region with these lattices.
Already it is showing up a little bit at 0.8, right? There is a
Yeah,
broad.
but up to this point we cannot, because one thing we can show that this is not, because the pion mass here is not actually physical it's actually 320 MeV. So you may expect it not happen exactly at 1 Fermi, but little bit higher distance. Okay, if it had been physical, then I would have set up, I can see some signal of saturation already maybe at these distances. But since the pion mass is very high here, it could happen little bit larger distance. When the pion mass goes to infinity, it will never happen. When pion
Yeah.
mass is little smaller, then it showed somewhere it should saturate. But we didn't go to that reason because we wanted to study the finite temperature part, finite temperature effect. That screening is not due to temperature, but it's string breaking and zero temperature.
Thank you.
Okay. Okay, so at short distance, there will be some zero temperature. There will be some lattice artifact because we're in finite lattice, and sometimes it shows up that there is this hypercubic symmetry of lattice will show up, which is relevant at short distance, and therefore we have to replace this short distance part. And the way we did is we replace this short distance.
One more question I wanted to ask you.
Yeah,
This
sure.
potential you are extracting from the Polyakov loop correlator?
No. Wilson line correlator. So some correlation function, and then we just propagate it, and then we have a. It's not Polyakov loop. Polyakov loop would have given you free energy, but it's as a Wilson loop with some finite time extent. Okay,
Does it have
Polyakov loop.
any issue like the Polyakov loop? I mean, there you have this cutoff effects like renormalization you have to do.
Exactly. That is right. So
Here
in
you
that,
have similar problem.
exactly, there will be a renormalization comes here, and that comes through the what is the additive constant in the potential that you have. Okay, because this potential is, you can think of like exponential of something. That renormalization is there even at 0 temperature, right? Finite temperature will not introduce any renormalization effect. Okay, so you can think of at 0 temperature the potential is like exponential of minus VRE times tau, and VRE plus something. VRE has a self energy correction, and that will give you the additive constant. So which is a renormalization that will basically shift the potential up and down. But since we are at a finite lattice spacing, all these renormalization constants are same, because renormalization depends on what lattice spacing we are in.
Okay, thank you.
And I will remove this additive ambiguity now in the next slide. So as I mentioned, the short distance part of the potential always contains lattice artifact, and we have to, and also the potential has a additive ambiguity. And the way we have solved it is at short distance, because the coupling is controlled by basically the 1 by r of the QCD, and the perturbation theory is useful in this reason. And we use the perturbative calculation, 3-loop perturbative calculation, just to replace the short distance part of the potential, which has a lattice artifact with the with perturbative part. Okay, and we use this perturbative, we use the 3-loop perturbative calculation here. But there is another issue with that, because this perturbative calculation will include all kind of momentum modes when we take the Fourier transform of the coupling divided by q square, and the mode which is near lambda QCD will give you a lot of contribution, and that is well known problem, because there is a renormalan in that case in the potential, because of coming from the mode, and we have to subtract this renormalan, and the way we subtract is we do not include those modes at all, and then we can calculate the potential which can match the lattice very smoothly, and that also fixes the um, um, arbitrary additive constant on the lattice. Okay, so we can use this perturbative 0 temperature perturbative calculation to remove these modes. Sorry, and here I show this potential again, but now we compare with this perturbative calculation, and you can see that this is what you would expect from perturbative calculation, and this is what lattice gives, this continuous curve, and this dashed line is the perturbative calculation, and you see the huge non-perturbative effect here. And again, on this in the case of imaginary part, I show you that there is the perturbative imaginary part is very smaller than what you would expect from the non-perturbative value. Okay, so really lattice is useful even in this temperature range to predict what is the potential. Using this potential, now we can get the spectral function. Here is the example of the spectral function that I showed the cartoon plot earlier, and this is the 0 temperature peaks of the spectral function. This is for eta c, so it is eta c, then the 1s, 2s, and this is for epsilon. Sorry, bottomonium eta b, 1s, 2s, and so. So this, we see that once we go to the finite temperature, the excited state peaks are all gone away, both for eta c and eta b states. But the 0 temp, the ground state peak shows is there, and there is a remnant part of it. And as the temperature increases, there is the width of this peak is increasing, meaning that there are chances of there is a larger decay width, so they melts immediately. And at 293 MeV, the peak width is so high for the case of charmonium, it is very difficult to talk whether we can associate it as a bound state part or it's a part of some quasi continuum. But in the case of eta b, we do see there is a remnant peak of the bound state. In the case even at 300 MeV, so it is not melted. So that is one of the important part result that we have got. This that the charmonium melts around 300 MeV, but bottomonium survives that temperature. Okay.
Of
So
course,
this is
here for the finite temperature case, of course, this is the dominant contribution, but there will be, for charmonium, there will be other terms which are more important, like spin splitting and all of these things, relativistic corrections. Yeah.
Exactly. Relativistic correction, actually, I want to do in my future plan, because for charmonium in this range, there might be important effect to it. Yeah. So this is what all about this singlet potential. Now I come to the octet potential that asked about. So again, say that you can a quark-antiquark in a singlet can absorb a gluon, go to a color octet state, and in this state we have to define a potential for this case, where we have a quark-antiquark pair separated by a distance r, and to project into the color octet, we just associate a generator of SU3 group, TA, Gell-Mann matrices, and then we have to calculate the potential of it. Okay, by using the same standard formula potential, doing analytic continuation, and then plug the potential there. However, the problem is the state is not gauge invariant. So how can we calculate on the lattice? The first thing we can think of that we have to fix a gauge. But there is a problem again that has been outlined in this paper, that if we have a Lorentz gauge, we can fix the Lorentz gauge, then we do not have a Hamiltonian. The transfer matrix does not exist with all positive node states. And therefore, we cannot decompose the Wilson loop into this pure exponential behavior in the case of Lorentz gauge. This is the problem even at 0 temperature. Then we have a Coulomb gauge. A transfer matrix exists, but as we know that Coulomb gauge does not fix the gauge completely. There is remnant, only time dependent degrees of freedoms are there, and we again get the expectation value of 0. Then we can fix a temporal gauge. Fixing the temporal gauge, we can show that it's a little bit hard to show here, but it can show that it will not give you a potential between a quark-antiquark in a color octet channel, but it gives a potential between quark-antiquark and the quark which is in the adjoint representation, which doesn't exist. So it's not the original system that we wanted to interested, but it gives some potential that is other than that. So at the present, there is no non-perturbative method is known that can calculate this octet potential at all. Okay. So the way we approach is this: we are associated with some gluonic field, HA. Gluonic field also transform under gauge transformation as a octet. So this whole thing is now gauge invariant. This TA, HA, when we contracted, their whole thing is gauge invariant. Now we can calculate the potential, but does this give the potential that we wanted to interested in? That is without the HA part. The answer comes from this diagram. So as r tends to 0, it can be shown that the propagation of this TAHA mode can be decomposed into a pure propagation of a pure HA mode times a propagation of pure TA mode. Okay, and this will get decoupled at short distance. So the potential, if we calculate from this whole propagation, will be a propagation of 2 modes, and the potential we can calculate from the TA mode by looking here.
Did you consider any kinematic range for this gluons? So it is magnetic gluons or soft gluons, or what are these? When does this decomposition holds good?
So there is no assumption about it. These
gluons in your second diagram in the boxes, these are all hard gluons, right?
This is at 0 temperature, right? This is at 0 temperature. This could be any gluons. It is, I'm not mentioning what is the energy of that gluon. There is no assumption on the coupling expansion of the hair. We are not assuming.
I was just wondering whether these gluons have, because these momenta are clearly much larger than lambda QCD. So gluons that are propagating in your boxes.
Yeah. So So do not focus.
Are always larger than lambda QCD, right?
The momentum will always be larger than lambda QCD if you want to calculate this in a perturbative language. But what I wanted to say is that even if you do not expand these diagrams, let's not expanding it. I just show this interaction for this, just kind of showing. But don't expand this. Just take this propagation TA separately. Then this potential is as r tends to 0 is a propagation of a pure octet channel plus a lambda h. Then if you expand it in leading order, then you get this 1/6 pi r, assuming that this scale is much greater than lambda QCD, so that you can do the perturbative calculation.
Yeah.
Okay.
In any case, at r tending to 0, it is all dominated by the hard gluons, right? So
yes, at r tends to 0, it is dominated by hard gluons. Yes, but in principle, you don't have to assume that that
Yeah.
it,
Means it is automatically taken care when you take R tending
yeah,
to 0.
exactly. Okay. So the trick of this calculating of the hybrid octet potential is that we calculate this potential H, which is called hybrid potential, that has been studied in literature, and take out the component which is independent of the BO, of the attached operator HA. That is what is the definition of the octet potential, and that is the only way to get octet potential from the lattice. And maybe I can skip this part because of the timing. So depending on the what operator you choose, you can put this state in different quantum number state. It could be so there is symmetry when quark-antiquark pair are separated by some distance. You can rotate it around that axis of separation. Then there is a CP symmetry. You can charge conjugation and then do a parity, that is a symmetry again. And then you can do a reflection with respect to the plane that containing QQ bar pair. And these are the symmetry. And depending on the symmetry, you can isolate this quantum state on this basis. And the operator that we consider is Bz and B plus, which is Bx plus Iby, and they correspond to the sigma u minus, which is can be read from here, and pi u. But for our purpose, we don't have to look into this notation. We just have to take the operator I choose is Bz and Bx plus Iby that project into quantum channel. And when h is equal to 1, it is just the standard Wilson loop that returns. Here is the zero temperature potential that we calculated. And for the first time, we see here at short distance, it's getting a potential which is color octet like a behavior, which is repulsive. And there is a tendency that it's merging together at short distance. But at long distance, they are different. Okay, because of and there is it's rising because ultimately this whole state Ta times Ha is gauge, it's color neutral, and the confinement should show up sometime. And this is just the same plot I have compared with singlet potential and compared with the Corsair lattice studies of other group. And this is the first time we could able to see actually there is a rise in the potential which is at short distance. Okay.
The long distance, it is more something different, which is nothing to do with the color octet. Only short distance, it is giving you the color octet part.
Yes, at zero temperature.
Yeah.
At zero temperature. What happens to finite temperature? The story is different. At finite temperature, here I show all this. So at zero temperature, the operator independence happens only at short distance, right? At finite temperature, here I have plotted the potential again, and we see that this potential, this octet potential becomes operator independent at all distances. And at finite temperature, we can call this potential as a octet potential even at large distances. So that is one of the fast calculation of octet potential at finite temperature. And not only that, it shows screening, and it merges with whatever you got from the standard singlet potential. Okay. And there is an imaginary part. Like a singlet case, there is an imaginary part is shown here. It goes to 0, but it goes to a finite value in the case of octet. Okay. And the reason for this is because at r tends to 0, it goes to 0 because when QQ bar is singlet, the gluons cannot see when the distance between them are 0 because they are color neutral. The gluon in the medium cannot dissolve the structure. But in the case of color octet, there is already a color charge even at short distance, so gluon can interact with it and make them decay. So this is the way we have calculated the color octet potential. And this is on the left side, this is the dynamic full Cohen's calculation. On the right side, it is the dynamical calculation, but it's still in the preliminary stage. So this is all about potential I wanted to say, and this is the summary of it. I showed that first ever calculation of the color singlet potential with this accuracy, the first calculation of this color octet potential, and this spectral function that we calculated, which shows that charmonium made earlier than bottomonium case. And one of the conclusion of that, hybrid quarkonia, the quarkonium which is in color octet state or hybrid, cannot be in a bound state mode in the QGP. So hybrid quarkonia cannot exist in the QGP phase. Okay. Okay, Shantan, how much time do I have? So
You can maybe wrap up in 5 minutes.
okay, so then I just show one thing that I have calculated in the case of photon rate. We have calculated also the photon rate calculation, which is just from a light quark, which is basically calculating the electromagnetic spectral function. And the photon rate is going to be proportional to the vector channel part, which is contracted with the G mu nu and rho mu nu. Rho mu nu is basically the electromagnetic spectral function. It has a longitudinal mode and transverse mode, but I'll not go into that, but I'll show the final result of this. Here is the final result of the photon rate. In the case, here is a 470 GeV MeV temperature for the Cohen's calculation, and these bands are the perturbative calculation, which is NLO plus LPM resummed perturbative calculation. And we see that as
Maybe
momentum,
you can explain this D effective and all of this.
D effective is calculating the spectral function of the photon at the sorry, maybe then I have to go to back here. So this is the rho mu nu, which depends on the momentum and energy of the photon that we are interested in. When omega is equal to k, that means we are on the light cone, and by extracting the spectral function and then calculating the spectral function at the light cone, we can get the photon rate. Okay, and the D effective basically is the spectral function at the light cone divided by this gen k mod k. Okay, it is called the effective diffusion coefficient, because if you assume hydrodynamics and at k tends to 0 limit, this actually gives you a diffusion, actual diffusion, position space diffusion coefficient. Okay.
So you mean for the vector current?
For the vector current, right? For photon, I am only interested in vector current. Yes.
Yes.
Okay. So in the case of 470 MeV temperature, we see that the photon rate is decreasing with momentum, and it's consistent with the perturbative calculation. Although the error bar is at short distance becoming larger and larger because of the spectral reconstruction process. But at finite temperature, we do see a clear difference between finite temperature full QCD. We do see a non-perturbative effect of photon emission. What is expected from perturbative calculation. So the photon rate tends to be smaller than perturbative calculation, and this non-perturbative effect we have resolved recently.
What is this crossover temperature here?
It's 180 MeV.
Oh, so it is within 1.5 TC.
Yeah, it's 1.2 TC actually, this temperature.
Okay. Mm-hmm.
And the way this can be understood, that the fact that it goes down inside the medium because of the thermal interaction, the quark actually gets an asymptotic mass. So these quarks are relativistic quarks, and they are propagating along the light cone, and they interact with the plasma, and they get an effective mass, which makes the photon rate smaller. Okay, so a massive particle radiates less. That is the simple explanation.
Yeah.
Okay, so now I just show one my
Sorry,
research.
what is that chi-q there?
Chi-q is the quark number susceptibility. It's basically if so I can show you where. So this, if you just look into the 0 component of this spectral function rho mu nu, okay, and then you just calculate the correlation function from it, it just became a constant, and that is what you call chi-q. This becomes constant because of the current conservation. Okay, so this rho 0 component is related to the chi-q. Okay. And okay.
So
and
that just cancels out in your thing, or is that some functional dependence that you have to keep?
Will cancel out. It will cancel out from it. It will cancel out from this chi-q actually down there. This chi-q and this chi-q will cancel out. But on the lattice, we calculate this directly because this chi-q take care of the extra denormalization of the vector current that is there, because you are in a finite lattice spacing. That's why we compute this on the lattice directly rather than photon, because of the renormalization factor.
Okay, thank you.
Okay.
Here you're not taking point split currents.
No. Here it's everything is at the zero separation. It's the point current. Because of the current conservation, we have
Oh,
to.
oh, that's why you need to take into account this renormalization. If you have split currents, then it would
No,
not.
then yeah. So if you are, as we are in finite lattice spacing, these currents are not conserved, this point current, and that's why we have a renormalization because of a word identity is different on the finite
Yeah,
lattice.
yeah.
Yes, but
Thank you.
yes, yeah. Okay, so this is all my research kind of some summary, and now I wanted to show what my future plans are. So as mentioned, the relativistic correction for the charm will be an important part of it, and the first relativistic correction the charm gets in the case of potential. So whatever we calculated so far is this V0R, and then there will be this 1 by m expansion of the potential as well, and this potential can be calculated by again a q-qubit pair separated by distance and interacted with the chromoelectric gluon electric field that is come from the gluon. And calculating this potential at connection at finite temperature will be important because at the Rick energies or LHC energies, the quarks are quite non-relativistic, relativistic, and this term will give you a significant contribution, will give you a better calculation of the quark charmonium spectral function. And therefore, if we calculate the Jepsi, then we have a better measurement, better prediction of the dimuon rate that is coming from the Jepsi. Okay, then I want to also consider the open flavor bound state that has not been even touched yet in a non-perturbatively gauge invariant way. There are models about it, but no first principle calculation about the spectral function of the open flavor, and it's difficult, particularly as if the quarks are heavy, then it propagates only into the around the temporal direction, but if the quarks are light, they tend to propagate along the light cone direction. So I wanted to do a first derive a differential equation here where a quark is propagating along the light cone direction by doing a chiral expansion like in chiral perturbation theory, and then uh, then we can then the 1 by mq expansion for this temporal direction, and then calculate the open flavor spectral function uh, that in the medium. And then melting of baryonic bound state can also be seen by easily extending this method, adjusting not only two Wilson line that is responsible for Wilson loop, but adding one more Wilson line correlator. Okay, so then I will come to the another important thing is the jet coenzyme that can also be connected to the Wilson loop. Is that, for example, this soft interaction of the gluon field with the highly energetic particle that is moving through the plasma can be written in terms of as a by optical theorem by as a cut of this self energy diagram. Okay, and this thing is related to a Wilson loop again, but this time the Wilson loop is not in the temporal direction that we consider for regular um, Quarkonia, but in the light cone direction. But on the light cone direction, again, there is a problem of analytic continuation. So we have studied how to do the analytic continuation for this tau part, but for the light cone Wilson loop, we have to also do analytic continuation in the velocity, because whatever we calculate on the lattice in the Euclidean velocity, but real physics in the real velocity. And therefore, we have to do this double analytic continuation to calculate this Wilson loop, and that basically take care of this soft resumming this all soft gluon interaction from the plasma non-perturbatively. This is related to this effect is related to not only to jets, it's related to the photon rate. Actually, this example I have borrowed from photon rate, so it has many application. One can calculate the jet transport coefficient using this Wilson loop. Not only that, if these gluons are if these lines are in the adjoint representation, Wilson lines are adjoint representation, then we can calculate also the gluon jet transport. So how a highly energetic gluon moving through the plasma lose energy. And this is also the first time we are aiming to calculate this quantities non-perturbatively on the lattice. This direction, it has not been touched in this LPM resummed way. So that is another thing. Then I also, in the later time, I would like to consider, those are two other immediate plans, but later time I would like to consider to going to finite density. For example, this is the QCD phase diagram, critical phase diagram, QCD phase diagram, and there is a conjecture critical point exists here. It's based on some that we have a first order phase transition predicted from model here, and QCD predicts there is a crossover, so there must be some critical point here. And it has been an active research program going on in Lattice and standard lattice calculations also. Now, one thing that I wanted to do is that calculating the photon rate near the critical point. The important of doing is that near the critical point, because of there is a fluctuations of lot of modes, we would expect the number of photons should go higher. So if we plot this photon rate as a function of temperature, if this temperature is close to the, or chemical potential close to the near critical point, we would expect a sudden jump in the photon rate. So from that we can give an estimate of the where should be the critical point, and tell experimentalists that please look into that region for a critical point. Okay. And later stage, not later stage, in parallel, I also like to explore the direction of machine learning and quantum computation. And the machine learning has been, I would like to use for the spectral reconstruction by using various effective field theories. So I would like to teach the network, the neural network, various properties of the spectral function, like what it should be from in the UV region, what it should be in the low omega region. Low omega region can be taken from effective field theory like transport theory, and UV region can be taken from perturbative spectral function. And there are also on the spectral function, there are these various constraint, like it should be positivity, it should be positive constraint, and it's strictly positive, or it satisfies some rules. And using this we would like to train the network first, then we'll apply this to the real lattice data. So for that I plan to calculate the correlation function with relativistic quarks, and just apply those data on the trained network and see what spectral function that we get out of it. And in later stage, I would also like to focus on this quantum computation approach for a spectral reconstruction, because in the quantum computation, we can directly calculate the evolution of a quantum state in real time. We don't have to go to the Euclidean time. And then the calculation of this spectral function will be just a Fourier transform of the correlation function. And so far, there are a lot of exploration what should happen at zero temperature, but there is no exploration in the finite temperature. One of the things that has been suggested is that we use the thermofield dynamics, which is like you double up your Hilbert space and construct a state like a similar to a vacuum state, and then you just propagate them in the real time and treat it like a vacuum state, and then just calculate all the correlation function using this state, and you get your thermal physics. And the thermal physics basically enter through this weight here, through the entangled state of this superposition of this n and n bar, where n bar is in the extra Hilbert space that we have introduced. So this way we can have more control, more benchmarking about the spectral function calculation from quantum computation. And for the moment, it is not possible to apply it directly to the QCD, but we'd like to apply for smaller systems like Ising model system or Swinger model systems. Okay, so this is my research plan. Thanks.
Thank you very much. So we will take questions. Any questions from the audience here?
So one question. So you showed in the previous conclusion, the rightmost, your, I guess, spectral function plot.
In the research plan, or?
No, you had some conclusion.
This one?
Yeah, here, the rightmost thing.
Yeah.
So you can compare this directly with experiment, can you?
No. It should be indirect, whatever, because it is at a given temperature, right? So if our cucumber system at a given temperature, but in experiment, it's evolving with the medium, right? The medium is evolving with gradually decreasing temperature, slowly.
Okay.
And we have to calculate this. We have to superpose because lot of temperature spectral function to get the final convoluted spectral function at the end.
So has
this
that
will
been
be-
done to see whether it describes the data or not?
No, not yet. The
Is
Quarkonia
that
level.
something that can be done? People have done it, so
There are some model dependent calculation, but it's not strict because this spectral function is difficult to calculate. So they take this model spectral function from various other sources and put into their hydrocode and just evolve it with the hydrocode, and then at the end see what could be the result. But not with this lattice calculated spectral function. This has not been done.
So we don't know how well any of these approaches describe the data. It's still not. It's still a work in progress.
I would say it's still work in progress, but,
Okay.
this is the first time when from pure QCD calculation you can
Okay.
think of.
Okay. Thank you.
Yeah.
Any question from the audience? Sorry, in the online audience. So if not, then we thank Dibyendu and thank you very much. So we end the session here.
Okay.
Do.